Yes, good morning again, everyone, and welcome to Argonne National Lab. This virtual tour, you will be able to use the chat feature, so please feel free to do so through the presentation. We'll be glad to respond to your questions. Thank you. And thank you for participating in this. You're going to visit this world-class facility and its dream team of researchers. And this year, the lab celebrates 75 years of delivering worldwide leading science and technology for U.S. prosperity, security, and economic growth. Today, Argonne designs, builds, and operates scientific user facilities, making the lab a multidisciplinary collaborative powerhouse conducting a broad spectrum of research to meet the nation's needs. Next slide, please. Its story begins with the Manhattan Project, led by Nobel laureate Enrico Fermi at the University of Chicago underneath the Stagg Stadium, where the first successful self-containing chain reaction occurred in 1942. Initially, the lab's mission was to develop nuclear reactors for peaceful purposes and to solve pressing national problems in science and technology. But since then, research and discoveries have inspired new technologies to meet national needs for sustainable energy, economic competitiveness, and security. Next slide, please. Next slide, please. Okay, this chart just shows you in more detail about that first experiment in 1942. So chartered in 1946 as the first national lab, Argonne is managed by the University of Chicago for the Department of Energy Office of Science. The laboratory director is Dr. Paul Kearns. Today, there are 17 national labs. Next slide, please. Located in Lamont, Illinois, in DuPage County, the 1,500-acre campus, about 3 square miles, has 100-plus buildings, some old and new, resembling a college campus. The lab employs nearly 3,500 full-time employees, representing 60 nations. 40% are scientists and engineers, and 10% are postdocs. It has an annual funding budget of approximately $1.2 billion and approximately 500 million in procurement. Research here includes basic science, that is understanding the natural phenomenon, and applied science, the practical applications of technological advances. This research requires sophisticated computational analysis achieved by supercomputers on site capable of quantum computing, machine learning, and artificial intelligence. Research scientists from all over the world utilize the tools available at 5 user facilities. 4 of them are on site. So right now you're looking at those facilities. Next slide, please. The first one is the Advanced Photon Source, which you will learn more about today in the following video. Next slide, please. Shows the Argonne Tandem Linac Accelerator System. Next slide, please. The Argonne Leadership Computing Facility. And next slide, please. The Center for Nanoscale Materials. Next slide, please. And the last one, Atmospheric Radiation Measurement Research Facility in the Southern Great Plains. Next slide, please. At this point, you can ask some questions. I got into the orientation very quickly as not to waste any time, but my name is Denise, and next to me is Dave, and he will talk about the actual instrument in more detail. So the video can follow if Angie's ready, or if you have any questions, I'd be glad to entertain those now.
Welcome to use chat, guys. We're watching the chat on the far side, so anyone has questions, please do come in.
Maybe after the video, they will have more questions during this process. All right.
There's an old saying, if you want to unravel a mystery, you need to shed light on it. Here at Argonne National Laboratory, we take that literally, using the brightest light we can create to uncover the secrets of science and nature. This is the Advanced Photon Source, or the APS as it is often called. It is one of 5 X-ray light source user facilities across the United States, operated by the U.S. Department of Energy Office of Science. Essentially a giant microscope, the APS is one of the world's most productive X-ray light sources, serving as a research destination for more than 5,500 scientists from around the world each year, who conduct about 6,000 experiments and publish about 1,500 peer-reviewed papers per year. Approximately 450 people work here, but the APS is a user facility, which means that thousands of scientists from around the world either make the trip here to Lamont, Illinois, or use our mail-in and remote access technology to conduct their research. Our collaborations with industry, academia, research institutions, and other user facilities at Argonne help drive the solutions and discoveries that further benefit our lives. From the microprocessors in your computers and smartphones, to next-generation energy storage for batteries and power grids, from clean and renewable energy technologies to drugs that improve your health, the APS impacts every aspect of your life and does so in an ongoing, positive way. What you are looking at is the heart of the APS, an electron storage ring so large that you could fit a Major League Baseball field inside it. The APS uses this ring to generate ultra-bright, high-energy X-rays, which help scientists discover new ways to develop energy innovations, create new materials molecule by molecule, and gain a deeper understanding of our planet, our climate, and the cosmos. Most people are familiar with X-rays. They're the same X-rays you may get at a doctor or dentist's office. But the X-rays generated at the APS are 1 billion times brighter, allowing scientists to peer inside materials with extremely high resolution. Scientists spanning essentially every basic and applied scientific discipline use these X-rays to improve our understanding of the world and improve our lives with new technologies. But how are those X-rays generated at the APS? Through a phenomenon called synchrotron radiation. The giant ring at the center of the APS is what is called a particle accelerator, and its job is to circulate subatomic particles, in this case, negatively charged particles called electrons, around and around. Accelerators are used for all kinds of things, from discovery science to cancer treatment, and they have been around since the 1920s. Scientists working on these early accelerators discovered that some of the energy electrons build up while circulating around an accelerator ring is naturally released as very bright light. This synchrotron radiation was considered a byproduct at first, but in the 1960s, scientists began siphoning off and using that light for research purposes. The APS, built in the 1990s, works on the same principle. We start with electrons generated by a cathode like the ones in early model television sets. Those electrons are then accelerated by high-voltage alternating electric fields down a linear accelerator, or a LINAC, and into a particle accumulator ring, where they will wait to be bunched together in batches. The bunches of electrons are then connected to the booster, a racetrack-shaped ring of bending and focusing electromagnets. Electrons will go around and around the booster, picking up speed as they go, until they reach just shy of the speed of light. Once they reach this speed, with an energy of 7 giga-electron-volts, the electrons are injected into the main storage ring, a circle of more than 1,000 electromagnets. The storage ring has a circumference of about 2/3 of a mile. Some of the powerful electromagnets bend the electrons in a circular orbit, while others keep the electron beam focused and small. In this way, the electrons will stay in the storage ring for many hours. Each time the electrons bend around the ring, they generate photons, basically very bright light. That light is directed down to more than 65 different beam lines around the ring, each one with experimental stations at the end equipped for different kinds of X-ray instruments. Once in the end stations, those ultra-bright X-rays are used to study different types of samples, which range in size from specks of dust up to centimeters of material. APS scientists use 3 different mechanisms, diffraction, imaging, and spectroscopy, to characterize the physical and chemical structure of these samples down to the atomic scale, and with time resolutions down to picoseconds, a few trillionths of a second. While the APS operates many of its beamlines, others are funded and operated by independent sources, such as companies, universities, and other research facilities. This is the experiment hall of the APS, where scientists assemble their experimental apparatus and carry out research. With 65 beamlines, the APS is essentially 65 discrete laboratories under one roof. The hall floor is made of 1 foot thick poured concrete, and there are no cuts or breaks in the experiment floor. This helps scientists who must align their experimental equipment to extremely precise tolerances, often less than a micron. For scale, a human hair is 70 microns thick. This is the APS Control Room, the brain center of the APS facility. This is where APS operators run the accelerators, monitoring every phase of the operation to keep it running efficiently. Electrons are continuously injected into the ring about once every 20 minutes to create a constant intensity electron beam. And these screens show the profile of the beam in the storage ring and which beam lines are running. Each research station has its own specialized set of tools and processes, each of them tailored for a different type of research, and different X-ray energy ranges are used to study different types of materials and systems. Let's go down and take a closer look at one of the beamlines of the APS. We are now at an APS beamline. This particular beamline focuses on materials science. If you want to build a stronger airplane engine or see exactly where the faults and cracks form in your material under stress, this is the place to do it. The beamline here makes use of the higher energy beams the APS can generate to peer into the structure of thicker samples, and can focus those beams down to micron sizes. The beamline then uses the precisely tuned high-energy X-rays in various techniques to study the composition and structure of materials of interest in real-life conditions, such as elevated temperatures and stresses. Because they are non-destructive and highly penetrating, APS X-rays can study materials under a variety of extreme environments. Here we see a device custom-built by the United States Air Force that puts high mechanical stresses on metal samples. The X-rays can peer inside those samples to monitor internal stresses and microscopic cracks in real time as they form. Scientists also have the ability to heat samples up to the melting point of most materials. Here we see a small furnace created for just this purpose. It wraps around the sample, and the X-rays can take images of exactly how the material reacts to both rising temperatures and stresses. These measurements are useful for creating new and tougher materials for a variety of uses, from cast iron skillets to airplanes and nuclear reactors. About 200 scientists from around the world use this beamline each year, either in person or by mailing in samples. Just like the other beamlines at the APS, the high-fidelity data collected here helps to keep us safer and build more efficient and durable materials. This is one of the beamlines associated with the Structural Biology Center, or SBC. It is operated by Argonne, and it's one of 16 beamlines designed to determine the exact structures of macromolecules, such as proteins and nucleic acids, that make up viruses and living organisms. Together with other APS beamlines, SBC studies the protein structures of infectious diseases, including COVID-19. Much of what we learned about the virus that causes COVID-19 came from APS data. With remote access technology and mail-in capability, the resources of SBC and other beamlines are available to scientists even during a global pandemic. This full-service beamline is able to grow crystalline samples of the synthetic proteins that infectious diseases deploy, a short walk away in the Advanced Protein Characterization Facility, and then examine those samples in incredible detail in the beamline, determining their exact shape and structure. Here in the end station, we see tubs full of liquid nitrogen containing crystalline samples. This robot arm picks up these samples and places them into the X-ray beam. As the X-rays diffract from the samples, the detectors record the diffraction patterns at amazing resolution. Using this beamline, scientists can test drug candidates, antibodies, and other potential treatments of infectious viruses, and see which ones inhibit them most effectively. Scientists, both from Argonne and from other institutions, have used SBC to learn more about Mycobacterium tuberculosis and malaria, among other diseases. The beamlines can also be used to answer questions about microbial life in various ecosystems, such as soils or oceans. As powerful as the APS is now, a massive upgrade of the storage ring is in progress. This upgrade will replace the existing components of the storage ring with brand new state-of-the-art magnets, vacuum systems, and technology. The effect will be X-ray beams that are up to 500 times brighter than those currently generated here. With improved focusing ability in some cases, this will enable more precise imaging, as well as significantly shorter measurement intervals and increased sensitivities to trace elements, which will open the door to even more discovery and innovation. With support from the U.S. Department of Energy and the thousands of scientists who use its capabilities, the APS will keep shining brightly for years to come.
Any questions at this point? Because otherwise we'll kind of do a review and tell you a few other things about the Advanced Photon Source if you don't. Okay. I don't see anything coming up on chat right now. So Angie, if you go to the PowerPoint, maybe we'll give a few ideas. So if you were to come on a tour out to Argonne and actually see or come out and work with us, which we do have, we've got high school students actually working with us, as well as college and universities and private industry, all coming out to do research. Our education department actually does a nice program with our high school teachers and their students, and actually can come out and use the Advanced Photon Source through a special program that you can sign up for with your teacher. So this is actually the administrative building that we have in front of the big circle that you're going to see in a few minutes, which is actually the instrument. But that's the administrative, that's where we do all of our training, our bringing in users to, and again, users are all those people that I just mentioned to you, universities and individual persons that need to redo research. Off to the right, you see a circular building, and that happens to be the convention center or the meeting center that we have. So if we have the next slide, please.
10:30. 10 minutes.
This, as you can take a look here and see a nice aerial view of the whole instrument. What you were just looking at is right at the bottom down there. That was the white building that has the administration and the circular building next to it, which is that convention center or center for doing meetings and all. But I'd like to point out there's three components to this instrument. In the middle of the circle, you see a line and a building. And if Angie, if you go up to that line, show the LINAC. The video showed a good example right there where the cursor is right now, is where the cathode ray gun is at, the cathode gun that shoots the electrons off. They travel down a series of magnets down that line, which we call the LINAC, and they go to the building in the middle of that area there. That building is actually where the attenuator and the accumulator is at, where they circle around, and by the time they do that, they get up to 450 million electron volts of energy. That means they're traveling about 99.99 the speed of light. After they get put into bunches, they go into the next ring, which is kind of an underground oval-shaped ring next to it. And Angie will show you how they go clockwise around here with the cursor. They will travel around that particular beam line several times until they get up to 7 billion electron volts of energy. Once they get up to that energy, they go into the building, which is right now where Angie's at, and they enter into the third part of the building, which is called the storage ring. So again, the LINAC was the first part. The underground oval-shaped circular building is called the synchrotron, and then they will travel around the big circle all the way around, and as they travel around, they will maintain 7 billion electron volts of energy. We've divided this up into 40 sectors. 35 of the sectors basically are used for making the X-ray beam lines. 5 of the sectors are not used, but they're used for virtually tuning up the electron beam, speeding it back up, and they're right next to that building. But when you see the triangular sprockets, like on the wheel, the very first one is to the left there. That's sector number 1. There are 35 of these sectors all the way around. So if you count each of the little triangular spaces all the way around, they're going to be, if you go back, Angie, just for a sec, those 35 sectors all the way around virtually go from sector 1 on the left-hand side all the way around to the right-hand side where the building with the white is on the top. That is sector 35. Each one of the sectors basically have two devices in them that will make the X-rays. One's called a bending magnet, and the other is called an insertion device. The bending magnet is about a 3-meter long dipole. It moves the beam over about 4.5 degrees. There are two of them in each sector, but only one of them is used for actually making the X-rays. The other one just bends the beam over. There are other magnets in there, by the way, also. They're called quadrupoles and sextupoles, which are basically used to focus the beam down, keep squeezing it and keeping it in a tight little traveling beam. So again, as they travel through that 3-meter bending magnet, physics has told us that in accelerators, if you have a light enough particle traveling near the speed of light and you move it, it will give off some of its energy. And that is the X-rays. This thing begins to glow X-rays. We open up a little window, and again, all those other magnets that keep bending the beam into the circle keep all the electrons inside the beam line, but the light comes out that window and travels down a 40-meter pipe to a building that looks like a one-car garage or a shed. And that's what we call our hutches. And it's in that position at the end of that beam line, we put our different samples, whatever the material may be, for whatever science it is. So that would, and as it travels down there, it's tuned up by mirrors and bending magnets and basically monochromic devices, which are able to focus the beam down to exactly the spectrum of the X-ray that we want to go into the sample. Right behind the bending magnet is the insertion device. And the insertion device is a set of permanent magnets. They're about the size of a billfold. And there's 50 below and 50 above. And they alternate north-south, north-south, north-south. And they wiggle the beam up and down. When that happens, we get even a higher intense X-ray coming out of it. We call them our intense X-rays or our super X-rays. And they come down that beam line. And so every sector, 35 sectors, have two beam lines, one coming out of the bending magnet and one coming out of the insertion device. So there is approximately 70 different beam lines. We use 65 of them presently, but there are 70 beam lines that can be working at any time, all the time. So there could be 70 different experiments being handled every time during every day. A couple of things I'd like to also point out is the white buildings at the upper portion of the wheel there. The one on the right-hand side is called CNM. That's Center for Nanomaterials. And then the one way at the top of the beam line, way up the top, is called the Argonne's Advanced Protein Characterization Facility, where we do a lot of our biology. So could we have the next slide, Matt? So I just put this one up here so you can see the diagram in the background of those three things again, the LINAC, the synchrotron, and then the big storage ring. And that's 2/3 of miles, they mentioned, 1,100 meters all the way around. And a little physics, if you take the speed of light, 3 times 10 to the 8th meters per second, divided by 1,100 meters, or 1.1 times 10 to the 3rd, good math problem, you get 2.72 times 10 to the 5th. That's how many times or revolutions an electron will make around that beam, or that whole big circle every second, 272,000 times. As every time they come through and they go through those bending magnets and insertion devices, they will give off X-ray beam. So the insert here, the inlet picture, shows the CNM, and it shows you that basically the tangential pipes coming out of the machine, that's what we're getting the X-rays coming out of that open window down onto samples. And again, the two things I showed you, the CNM, the Center for Nanomaterials, and the Advanced Protein Characterization Facility, the major reason they're here is because these X-ray beams can go all the way down to 10 nanometers. We can see down to the atomic level. So that's basically, next slide. The only reason I like to show this slide is very small to see, but you can visualize it later if you want to take a look at it closer, if you have the capabilities, or we can send it to you. But anyway, what this is showing you all the different colors. Now the legend in the middle of the thing tells you biology, chemistry, physics, nanotechnology. It tells you all the different types of things that go on. The sector 1 that you see that we just showed you in the lower left-hand corner basically is green and yellow, and that basically would mean that it's physics and material science. If you look up by where the Advanced Protein Characterization Facility is, at the top, you see a lot of blue. Well, that's all biological life science beam lines that you see there. And our beam lines, our sectors are either run by Argonne people. Then in the case of that case, if you ever look at that picture, it says XSD, that means X-Ray Science Division. And if it's run by a group of outside people, people that actually pay to come to work at it with our instrument, it's called a CAT team, Collaborative Access Team. A good example of that is Sector 5, which is D&D CAT. And D&D CAT basically is Dow, Northwestern, and DuPont. And those are three chemical companies who have been with us since we opened up 22 years ago. And that basically is, they do protein character, they do polymer plastic research there. If you go up to sectors 13, 14, and 15, area up there, those are called CARS. That's the University of Chicago, Center for Advanced Radiation Studies. One is called GSE CARS, which is Geology, Soil, and Environmental. One is called BioCARS, and that's biology. And then one's called ChemCARS, which is all materials other than that. And then you go over to the other one over in Sector 26 it is, and that's going to be the Center for Nanomaterials, and that's CNM. And again, the main reason that's there is because of the beam line coming out of there is called an X-ray microscope. Okay, are there any questions at this point? I don't see anything coming up on the, here's one from Sebastian. How long does it take for the electron beam to travel through all the sectors? Nanoseconds. Okay, again, it's traveling at the speed of light. So you're in the, you're again 272,000 times every second. It goes 272,000 times that whole big circle every second.
That's like traveling in your car 186,000 miles per second, not per hour, per second, if that puts it in another perspective for you.
Any other questions? You're welcome, Sebastian. Here's one from Keaton. What disciplines are the beams most commonly used for? Okay, well, if you can tell by the colors there again, there's a lot of blue, a lot of biology, but I don't want to think about that because a lot of it is very intensely, the other colors there are very, very important. Material science, in whatever disciplines you can think of. We've had things, I don't know if you noticed the one picture there where there was, we studied in Sector 1, we actually studied turbine blades for jet engines. We have another whole beam line that does nothing more looking at sprays coming out of fuel injectors to try to improve diesel engines and car engines to have more miles per hour, or better combusting capabilities. So any science research there is, that's all there is to it. So if there's any final last question, we're pretty much at the end of the session today.